So good morning, everyone. So welcome to the second invited talk at ICFP. So the talk is going to be given by Christos, and Christos Dimoulas is an associate professor of computer science now at Northwestern University, and he completed his PhD at Northeastern University with some guy named Matthias Felleisen, I think. Yeah. So he completed his PhD and he worked there on the foundations of contract systems. So after the PhD, he joined Stephen Chong's group for a postdoc at Harvard, where he dove into security-related issues, designing, implementing security contracts. And since then, he's moved to Northwestern and he keeps thinking about the theory and design of contracts and gradual types. And spends increasingly time on trying to understand programming language pragmatics. And that's also the topic of his talk. It's called the rational programmer. And Christos will tell you all about it.
Hello, everyone. So I would like to start the talk with an incontroversial, I believe, statement. So one goal of PL research should be to help us understand, analyze, and improve PL design. I hope we all agree about that, okay? So over the last 60, 70, 80 years, the PL field has developed two broad ways to understand design. One is theoretical, the other is from the practice side. And I mean these two labels in a very, very broad way. So on the theory side, I have pretty much everything that uses formalisms. On the practical side, I have everything that involves realizing languages as artifacts and understanding how they are used, including implementation, corpus studies, human factors, and so on. Okay? Here comes the controversial statement. I believe that supporting PL design is a very hefty task. And just relying on these two pillars is not enough. We need something else, okay? And what I'm going to try to argue today is that we actually need something else and what I believe this something else is, okay? So to do so, I will start by telling you a little story about a little language called TypeScript, okay? So TypeScript, as we all know, is extremely popular. It's actually the language that rises in popularity the most for a number of years. And another possibly controversial claim is that TypeScript is the crown achievement of PL research of the recent years. And why do I claim that? Because TypeScript aims to use our precious types, okay, to make sense of the wild world of JavaScript, okay? So I'm going to give you a very, very simple example to show what I mean. Here we have a little JavaScript module. We have a function called logitem. It consumes an argument x, and then tries to print it after trying to turn the x into a number that has two decimals, okay? Of course, as you see, what we are passing actually to logitem is a string, which means we are going to get a runtime error because strings do not have the toFixed method. Okay? So if we try to write the same program in TypeScript, we can use types to express our intention that this logitem function is going to use. It's going to consume both numbers and strings. Okay? And even though this is a toy example, what is interesting about that, and actually the TypeScript compiler is going to give us a compile time error. But what is interesting here is that this is a true union type, okay? And for decades, we have been told that programmers do not want to use things like union types, okay? But now they keep using them again and again. And actually, if you look at what types means in the JS plus types part of TypeScript, you will see that pretty much is a collection of ideas that go back to 50 years of research in PL. All the interesting features of the TypeScript type system, we can trace them back to things that the PL research community has been studying for half a century, okay? and their combination is extremely challenging. So, for instance, these are two of my favorite papers from the late 80s, early 90s that are trying to make sense of languages that have some subsets of those features. Okay? And 30 years later, this is a paper from last year's POPL that tries to actually push the frontier further about how we understand the principles of languages that come with such rich features as the ones that you find in languages like TypeScript. Okay? So basically, what I've told you so far is that JavaScript is a triumph of PL research, powered by PL theory. Okay? But is it really? Because PL theory tells us that a meaningful type system is one that's a sound prediction mechanism. You know, the most famous theorem, type soundness. TypeScript is not type sound. Okay? And we can even use this, yes, it's not type sound, and we can even use this very small example that I have here to show why it's not type sound. Okay? Let's just change a little bit the type ascription on the parameter. Let's make it be a number. This should make it harder, if we were in a sane language, to call this function. We shouldn't be able to pass a string to that function. But if we run this program, the type checker of TypeScript does not complain. And what we end up getting is actually a runtime error. Okay? And why is that? It's because of the any guy there that basically washes away anything about the 42 being a string and allows us to use the 42 anywhere we want, okay, including as a number. Okay, so this is not, I want to emphasize, this is not a theoretical issue. Any is everywhere, okay? All the built-in libraries of TypeScript use any pervasively, okay? And it's not just any. There are so many other issues of unsoundness inside TypeScript. Okay? Any is just the tip of the iceberg. In fact, the one that hurts more for me, the one where things get worse, is that TypeScript promises to give a seamless interaction between TypeScript and JavaScript, is untyped sister language, okay? But it doesn't really, okay? So this is the same example that we've seen before. I have refactored it a little bit differently. So what we have at the top is the definition of log item as in a TypeScript module, okay? And what we have at the bottom is the use of log item in a JavaScript module, okay? And if we run that, just like before, when we used any to wash away that 42 is a string, we'll see that when we have interaction between TypeScript and JavaScript, types mean nothing, okay? So yes, TypeScript is JavaScript plus types, but the flip side of that is that TypeScript is also JavaScript by the delete key, okay? And again, this is not a theoretical issue. This is an issue that has practical significance. This is the GitHub page of Definitely Typed, a massive repository of type interfaces for JavaScript libraries so that we can use them as if they were typed inside TypeScript code. Okay, you can see that they have, what, 35 million, is it 35? Yeah, 34.4 million users, right? And they say themselves that this is a repository for high-quality TypeScript type definitions. But corpus study after corpus study over the last few years has shown us that many of those are wrong, okay? And the reason they're wrong is because there's nothing that checks what's going on with them, right? The interaction between JavaScript and TypeScript is unsound. Okay, so the problem is not just theoretical. Again, it's a practical issue. And in fact, when human factor studies also tell us that at some level at least, developers recognize that, okay? And they say that they would prefer a sound word. So even though there are all these problems, why is TypeScript so popular? Okay, here is an explanation. it helps programmers in certain contexts. It helps them when they're trying to use their IDE for auto-completion. It helps them when they're trying to debug. So even though TypeScript is unsound, even though types in TypeScript interfaces are wrong many, many times, in certain contexts, TypeScript's type system produces actionable information that can help developers make decisions. OK? So what is this information? That's what we should be asking. And how does it translate to actions? In order to understand TypeScript, this is the question we need to answer. And this is exactly the moral of the story. This pillar that is now shaded is exactly the thing that we're missing in order to understand TypeScript and why it's so successful, and PL design in general, OK? And this pillar is something that I call PL Pragmatics. So pragmatics is a little bit of an overloaded term, so I will try to define it. It's a term that is gleaned from the study of natural language, from linguistics. It's a discipline that started about 100 years ago. It sprang out of the study of semiotics. Okay? Charles Morris is one of the pioneers. He's actually a graduate of Northwestern, my university, in 1906, I believe. Okay? Since then, pragmatics is part of the canon of linguistics. This is a textbook that is taught in undergrad classes about linguistics. And of course, the ultimate success, pragmatics has a Wikipedia page, okay? That very nicely summarizes what it is about. It is basically the change in meaning that happens to utterances of natural languages occurrences in particular contexts, okay? And just like the linguistics field has developed systematic ways to analyze and understand semantics, what I think we should be doing is also discover and develop systematic ways to understand and analyze PL pragmatics. So I'm not the first to suggest that. The first person who actually talked about PL pragmatics is Charles Morris's student, Jim Morris, okay, in one of the most beautiful seminal PhD theses ever written, okay? So Jim Morris actually said that what matters when we study pragmatics, when we study programming languages, is pragmatics. He was saying that to contrast with the predominant wave of denotational semantics back in the day, okay? But Jim Morris ended up defining pragmatics as the observations that any observer can make when they look at the execution of a program, okay? And from there, he ended up defining some very early versions of operational semantics, and of course, contextual equivalence. So instead of talking about pragmatics, he ended up talking about semantics. So here is how I understand pragmatics, okay? So semantics is all about the intrinsic meaning of a language feature, and I use the term language feature in a very, very broad way, okay? It's basically the meaning of the language feature in any context. And we can describe this formally with theorems like type soundness, determinism, no undefined behavior, and so on. Pragmatics is what happens to this meaning, okay, when we are trying to use this feature in a specific context, and whether trying to use the feature in a specific context results in extra actionable information, okay? Let's make it concrete. The type system of TypeScript, the intrinsic meaning, 0, okay? Because type soundness does not hold, okay? But when we try to use TypeScript types to decide what method we should call, okay? When we are trying to decide how we are going to refactor the code, there is some extra information there that helps us make decision. And this positive delta is exactly what pragmatics is about. Of course, pragmatics may also result in a loss of information. For instance, if we are talking about JS, it has this very nice semantic property that a lot of its primitives never give us an error, okay? But of course, if we look at how this affects the process of debugging, we are losing information. So pragmatics in this case has a negative delta of information, okay? So studying pragmatics actually means when developing tools that help us understand these positive and negative deltas, okay? I think at this point, many of you may be wondering about the following. Why don't we just ask programmers to tell us about the actionable information? Why don't we do human factor studies? Okay? So the reason that I say we need something else besides human factor studies is because if we do that, we'll be basically asking together 4 different questions. Does the PL produce relevant information? Is this information actionable and how? Are the programmers able to understand that information? And do they tend to use it as intended? Okay? The last 2 are squarely outside the scope of pragmatics. It is exactly what we should use human factor studies for. The first 2, though, I claim that they are all about pragmatics. Okay? And just like we don't need to ask humans when we are studying the theory of programming languages and type soundness, I think we can study actionable information without humans too. Okay? So in the rest of the talk, I'm going to tell you about one way that I have been working on for the last 6-7 years to study pragmatics, my instrument for studying pragmatics. Okay? It is an empirical method centered around large-scale automated experiments. By the way, I want to say, and I want to emphasize, this is just one way. I would consider it the utmost success of today's talk if some of you get intrigued and go out there and come up with your own ways to study pragmatics, because studying pragmatics is what I think is the most important thing about this talk, not so much my method. Okay. So let's go to the method. My method is called the rational programmer, and it's actually a recipe for constructing large-scale experiments. Okay? So the first thing that we have to do to kickstart the method is basically pick a feature in the context. Okay? For example, mixed types, like the ones that we've seen before in the examples in TypeScript, and tracking down bugs. Okay? A particular context. In fact, this is an actual experiment that we have run and published about, and it's going to be the running example that I'm going to use through the rest of the talk to make everything concrete. So after we pick a feature in the context, the next step is to basically formulate a hypothesis, how the given feature produces actionable information in the given context. Okay? There is something, though, that needs care here. The rational programmer asks that the hypothesis should specify a specific, well-defined strategy for using the feature in the particular context. Once we have the hypothesis, we turn the strategy into an algorithmic procedure. And this algorithmic procedure is what I call a rational programmer and gives the name to the method itself. Okay? After we create our rational programmer, we create a population of scenario relevant to the context that we have. We feed them to the rational programmer. We obtain our data, and then we analyze it to refute or validate our starting hypothesis. Okay? I'm going to show you exactly how to instantiate this recipe with the running example of mixed types and tracking down bugs. But before I go there, I want to talk a little bit about why we call this method the rational programmer. Okay? So the idea behind the rational part is basically inspired by a long-standing tradition of understanding decision-making using rational agents. Okay? And in particular, the version that the rational programmer is based on the work of Herbert Simon and his idea of bounded rationality, because rational programmers are agents that are not omnipotent. They can do anything, everything. They don't look for global optima. Instead, they're trying just to complete the job as well as they can. Okay? the programmer part is not supposed to indicate a real programmer in any sense. Okay? The rational programmer, I want to emphasize that, is not a model in any sense of human behavior. Okay? In fact, just putting the word rational next to programmer is an oxymoron. Okay? What the rational programmer is a device that stands in for the programmer in order to allow us to understand the systematic connections between PL design and the information that it produces in particular contexts. Okay? Cool. Okay, so let's go back to the running example about mixed types and tracking down bugs. We're going to instantiate the recipe. The difficult part is formulating the hypothesis. In order to do that, we are going to start with some research question that relates mixed types and how they affect tracking down bugs. And we are going to start with the most vague and simple formulation of this question, and we are going to iterate to make it more and more precise. Okay? The first problem with this question as it's phrased here is that it's unclear what we mean by mixed types. Okay? So the first thing that we have to do to make it precise is to specify what part of a mixed type system do we have in mind. Okay? And in particular, in this case, I'm going to focus on the enforcement mechanisms. What happens when typed and untyped code interacts, and how the language enforces or not the types at the boundary between typed and untyped pieces. Okay. So you will allow me to open the first parenthesis of the day, okay, just to explain the spectrum of enforcement mechanisms. Okay, I have a little bracket program here. This is the schematic of the program. It consists of 3 modules. We have the client, who is using a library, JSON unpack, that it's using basically to get some JSON data that it has and marshal it in some specific data structure. And then the client also uses another helper module where it passes the unpacked JSON to be summarized. Okay? It's very easy to turn this program from a racket program into a typed racket program, bring it from the untyped world to the mixed typed world. There are many, many ways we can do that. I've picked one. The first thing is that basically we now have an interface between the client and the JSON unpack library. Okay? This interface basically specifies the type for the exports of the JSON unpack library. Okay? It's exactly like what happens with definitely typed in the TypeScript world. Okay. I don't expect you to read all the racket code with more parentheses. Okay? What I want to point out here is that now JSON unpack has a type that says it's a function that consumes a JSON expression plus a string, and it gives us back a list of hash tables that map strings to anything. Okay? This enables basically the client to see the library as if it was typed, even though it was never typed. The second change that I've done to bring the program that we had before to the mixed typed world is that I have typed client summarize, the helper module. And I've done that actually for real this time. I went in there and I added a type definition, and I also added a type annotation for the single function that the module defines. Okay? So what's going to happen now is, because we moved from the world of racket to the world of typed racket, the type checker of typed racket is going to kick in. And at compile time, it is going to basically check all the blue code and tells us if the blue code is consistent with itself. Okay? In this case, it is consistent. But I have a bug. Okay? If you look at the code, the red parts, you will see that this function promises to return a list of hash tables, but instead, it returns a list of association lists, okay? A different data structure. My type checker cannot catch that, because this is an inconsistency between untyped code and the interface, okay? And exactly what is going to happen next depends on the enforcement mechanism that we have, okay? And there are options here. I'm going to show you 2. There are many more, but I'm going to show you just 2 today. The first one is what I call the tedious academic, okay? It's the natural semantics that prioritize soundness, What happens in this case is that when we have values that go from the typed word to the untyped and back, those values are wrapped in proxies that enforce the expected types, okay? Which means that basically the function JSON unpack, because it goes through the interface, when it flows inside the client is not going to see JSON unpack itself. It's going to see a proxied version of JSON unpack. And when this JSON unpack returns something that does not match the type, we are going to get an error, okay? At runtime, but still an error that points exactly to the problem with the interface, okay? And not only that, the error is going to give us a little bit more information. It's something that we call blame. That's going to track, it's going to point the mistake back to the disagreement between the interface and the implementation of JSON unpack, okay? Of course, you can imagine that all these wrappers and all these layers of indirection and all this checking that is happening affects performance. And this is the reason that the second approach that I call the approach of the practitioner, which is what TypeScript implements, goes with what we call the erasure semantics, okay? JavaScript by delete, okay? And exactly this is what happened with TypeTracket. TypeTracket by default offers natural semantics, but you can also opt out and have something like erasure semantics. In which case, our blue code, the helper module, when it compiles, it's not going to have anything related to types anymore. And what we are going to be running basically is the racket program. So the faulty value is going to flow here. We're going to treat it like a hash, and hashRef is going to complain. And if we are lucky, we are going to get a stack trace. That gives us some information about what's going on here. OK? OK, cool. So we have one syntax, one type system, and two different semantics, each with its own error reporting mechanism. So I want to point out also that I'm using TypeTracket, even though we started talking about TypeScript, because the type system of TypeTracket is similar to that of TypeScript. OK, I'm closing now my parentheses. OK, everything is balanced, and we will go back to the recipe. So now that we talked about enforcement mechanisms, we can go and refine our question. And we can say, which semantics plus error reporting mechanism produce actionable information in the context of tracking not any kind of bugs, but type-level bugs, like the ones that we've seen before. OK. In order to have a hypothesis, though, that is usable for a rational programmer experiment, we need to say exactly what actionable means. We need to be able to specify a strategy, OK? And that's exactly what we're going to do now. I'm going to introduce this notion of localization scenario. This is basically a configuration of a program where some parts are typed and some parts are untyped, OK? A mixture of typed and untyped modules like the ones that we've seen before. A localization scenario is not just a mixed program. It's a program that when we run it, it's actually going to give us at runtime a type error, OK? And our goal is to use the information from that type error to add more annotations to that program so that we can push the error inside the type region, OK? So that at the end, we reduce our localization scenario into another configuration that fails statically at compile time, OK? Because presumably, static errors are easier to track down than dynamic errors, OK? So how do we do that? One way to think about what we're looking for is basically to navigate through the lattice of all configurations of this program. And we can use the error reports to do this navigation. Error reports point to some module in that program that we believe is somehow related to the problem that we see. So we can go to that module and add types. And we can keep going like this until finally we reach at the point that the dynamic error goes away and is replaced by the static error. OK? So let's see. By the way, this is a projection of a series of theoretical results that I have worked on with my collaborators over the years. In fact, on Thursday, the latest result on that which is a collaboration with Hongyu and Robbie Findler, who's over there, will be presented at UPSLA if you are interested in this kind of theory of contracts and gradual types. Okay? So I call this a successful error trail, because basically it's like we are following a path based on the error all the way from the initial scenario to a much simpler case. Okay? And it's successful if we finally get to the point where we get this static error. Okay, let me show you how this plays out concretely with a running example. What's going to happen here is basically the faulty value is going to give an error. Blame is going to point to the interface between JSON and PAC and the library. We are going to type check, we are going to add types to the library now, and type checking is going to fail, which means we finally managed to produce a successful error trail. Of course, this is not always the case. We can also fail to reach a green state here. And this can happen, for instance, in erasure. We can have the same program as before, the same bug. What's happening is we're running basically racket, and then at the end, we get an error inside client summarize. The information is not particularly useful in this case. All we can deduce is that we have to go and add types to client summarize, but client summarize is already typed, so we get nowhere. Okay? So now that we have this idea of error trails, we can finally state a precise hypothesis that is suitable for experimentation with a rational programmer. Given two mechanisms, A and B, like the natural and the erasure semantics, for most scenarios that we have in a population, we expect that A is more successful in terms of error trails than B. Okay? Now that we have the hypothesis, the next step is to go and actually create the rational programmers. But in this particular case, what I'm going to do is I'm going to first go and create the populations, because this is going to help me make my life easier when I'm trying to define the rational programmers. Okay, so in order to create the populations here, we need to create a lot of localization scenarios, which means we need diverse and a great number of type errors. Okay? So unfortunately, there is no corpus in the wild that is suitable to use for that. So instead, what we've done is we took advantage of the amazing work that Ben Greenman has done, who created a diverse set of benchmarks of gradually typed or mixed typed programs. Okay? And then we took advantage of another line of work on mutation and dynamic adaptation to basically turn those type correct programs into millions of programs that have inside them type level errors. Okay? In fact, we have so many of them that at the end, in order to get a representative sample, we end up with 100,000 scenarios for our experiment. This is the corpus of our population. 70K of those correspond to type level mistakes inside the code. 30K of those correspond to type mistakes inside interfaces, like the ones that we've seen, the mistakes that we've seen indefinitely typed. Now that we have the population ready, we can go back and discuss about how we can turn our hypothesis into a rational programmer. And the population plays a role here because in order to turn the hypothesis into a rational program, into an algorithm, we need to make two decisions. Where to go next, okay, which we have already discussed. This is where the error points us. But we also have to know what types to add, okay? And here is where we take advantage of the population, because the work that Ben has done basically includes all the types for all the components, all the configurations of those benchmarks. So we can just simply go and get them from the benchmarks and use them where we need them to navigate this lattice. Okay? So in fact, in our experiment, we don't have a single rational programmer. We have a rational programmer that uses the natural semantics. We have another rational programmer that uses the erasure semantics. We have a third rational programmer that uses the natural semantics but ignores blame and uses exceptions. And this is very useful because it's a baseline to understand the value of blame, to isolate it from all other confounding factors. And we also have a fourth rational programmer, which is basically doing random moves, and this is used to debunk the null hypothesis. Okay? So now that we have all these 4 rational programmers, we can feed them with our population of scenario, and after a lot of compute power and waiting for 4 to 6 weeks, we finally get our data. Okay? So what I want to do now is give you a glimpse of that data. I'm going to use this kind of plots that I call versus plots. Basically, they show us how one rational programmer A, fares against all other rational programmers in the experiment. The y-axis is percentage of scenario. The x-axis is basically the different rational programmers, where you see a green bar. The height of the green bar means that rational programmer A succeeds for this percentage of scenarios, whether the corresponding other rational programmer fails. Where you see a red bar, it's the inverse. The other rational programmer succeeds, where the rational programmer A fails. Of course, 2 things to observe. The first one is that the first position for rational programmer A versus rational programmer A is 0, because basically it's tied with itself. Okay? And of course, the bars, the red and the green bars, do not add up to 100%, because there are scenarios where both of them succeed or both of them fail. Okay? So let's move to the actual data. And here I have 2 versus scenarios of the natural rational programmer against everybody else. And I have 2 plots because I have divided the code bugs versus the interface bugs, the 70K scenarios in our population that correspond to code bugs versus the 30K that corresponds to interface bugs. There are a few things to observe here. The first one is that the random rational programmer beats the natural rational programmer. This is not a surprise, okay? Because the random is going to try everything until it exhausts the whole program. At the end, the whole program is going to be well typed. The program has a mistake, so the whole program is typed. We know that it's ill-typed. At the end, we're going to get a static error, okay? The other thing, but there is something that basically tells us that the natural rational program does better than the random. We have also measured the number of steps, the number of modules that the natural programmer needs to add types to, and the distribution of those is much more skewed towards the small numbers than that for the random, which is more like a normal distribution. Okay, so another thing that is worth pointing out here is that for code bugs, the natural programmer beats both erasure and natural exceptions, but it's as difficult to beat erasure as it is to beat natural exceptions. Okay? When we go to the interface bugs, it becomes much easier to beat erasure, to beat natural exceptions than to beat erasure. Okay? So basically, what we are seeing here is that blame matters a lot for the effectiveness of the natural programmer. Okay? The other thing I want to point out is the scale of those 2 plots. One is just 12 there. The maximum is just 12. So if we are looking at code bugs, actually what the natural programmer offers us, the natural semantics offers us over erasure semantics is not that much. Where the natural semantics makes a lot of difference is when we consider interface bugs. Okay, there's one more piece of data that I want to say, that if we look at all the RPs and the detection rates, how many bugs they actually find, not whether we can get those bugs and turn them into static type-checking errors, then all RPs have comparable performance. Okay? That means that we can use erasure semantics, we can use natural semantics, and if we care about just finding bugs, not tracking down the location of those bugs, then it doesn't matter which one we use. Okay, so to put everything together, natural semantics with blame is the best, but not by much, and not in every case. Okay? Natural checks without blame not much better than Erasure, at least when it comes to actually tracking down bugs. And Erasure in practice seems to be good enough. We have an edge with natural if we're trying to track down these type interface bugs, but if we care about detection or we care about code bugs, then Erasure is okay. Okay? So we have some evidence now through this analysis of the pragmatics of these mechanisms, of these enforcement mechanisms, that TypeScript is not such a crazy idea after all. Okay? And there is another thing that we learned from this experiment, that some of the work that has been happening in the theory of gradual typing is basically ignoring the value of blame, which basically creates a blind spot for that theory. Okay, so of course, this is an experiment. All experiments have threats to validity. And maybe the most important here, just to close the loop with TypeScript, is that I've used Racket and typed Racket, and Racket is not JavaScript. It does not have the same semantics. Okay? The experiment cannot, the results, the conclusions of the experiment cannot be safely projected to JavaScript. Of course, this is a limitation. If we want to draw conclusions about JavaScript and TypeScript directly, we have to repeat the experiment in that setting. I want to take a step back now and talk a little bit about what we learned from the rational programmer. So the rational programmer is basically a way to state hypotheses about PL design and try them out. When those hypotheses hold, we get back strategies that we know they work, okay, about how to use a particular feature in context. And those strategies can be used to improve tools, to bootstrap the use of these features, and also they can be used to improve documentation. Okay? The other thing that we can do is we can use these strategies to teach people how to use features. And also, we can try, after we teach them, to check whether actually they like these strategies and they are able to make them work. Okay? I want to say a little bit more about the teaching. The strategy that I just showed you for following error trails is exactly how I've been teaching my PhD students and undergrad students how to use contracts and how to interpret blame when they work in typed Racket and Racket with contracts. Okay? And I want to make a bigger point. Matthias Feleisen and I are working on revamping a PL course based on pragmatics. Basically, we will be looking at how the evolution of programming languages can be justified through the lens of pragmatics. Matthias is teaching actually the Canary version of this course right now at Northeastern, and I'll be teaching the next version at Northwestern in the winter. Okay, of course, hypotheses can be refuted by the rational programmer. And in this case, even though we cannot really prove the absence of actionable information, remember, we just look at one particular strategy. There might be others. What we can do, if this strategy basically captures some assumption about the feature and how it works, we can invalidate those assumptions, okay? And of course, we can go back to PL design and implementation, and if we think that actually this is critical, we can go and revise our design and implementation and restart the whole cycle, okay? In fact, I want to make an even further claim here that the rational programmer experiments are in a dialogue between PL design and implementation and instruction in human studies, okay? When we succeed with a hypothesis and we validate the hypothesis derived from the design with a rational programmer experiment, then what we can actually do is try it with instruction, try to teach it to people, and try to do human studies. If those fail, this is a sign that maybe we need to go back and revise our hypothesis. And maybe this will also trigger revising our PL design and implementation. Okay? I have given a very rosy picture of the rational programmer. I want to tell you the ugly truth also now. There is a price for these rational programmer experiments, and it comes in terms of time and effort. Okay? We have run 4 full experiments so far, and we are halfway a 5th one. Each one is a challenge. We are getting better. We are able to reuse more and more of our experimental infrastructure. But overcoming the experiment-specific challenges always takes a lot of effort and energy, okay? And actually, the reason I mention that is because I actually want to say that this is not just my work, okay? There is a group of people who have believed, a small group of people, who have believed in this work and have helped me realize these ideas and bring these experiments to fruition, okay? And I want to thank them. In particular, I want to thank my 2 PhD students, Lucas Lazarek, who graduated last year and whose dissertation involved the first 3 experiments that we did with the rational programmer the rational programmer method, and Nathaniel Hezuk, who has received the mantle after Lucas graduated. And of course, I would like also to thank Matthias, who encouraged me to continue down this crazy path when I presented to him in his office right before I left from Boston to Chicago, and since then has become my co-conspirator for everything related to the rational programmer. And last but not least, I want to thank the people that are behind Racket, who are over there, who have dedicated their life into producing a polished and very interesting language that is both the source of inspiration for all this work, it's the object language that we study in this work, and it's also the language that we use to implement all the infrastructure and do all our data analysis for the rational programmer. If you want to learn more about the rational programmer, there's a CACM article that presents the whole vision. I think it was out this July. If you want to learn even more than that, go to my website at Northwestern. You will find an extended version of this article because we had some space limitations. And you can find also the full collection of the technical papers about all the experiments we've done. I want to leave you with a final thought, okay? If I want you to remember something from this talk, is that PL pragmatics matters, okay? And the PL community, the PL research community, has neglected them for a very long time, okay? So this talk is basically a call to action for all of us to think about pragmatics and try to figure out ways to develop them into a discipline that is as robust as the theory and practice of programming languages that we have been developing for the last 80 years. Thank you.
Questions, please.
Hi, Harry Goldstein, University of Buffalo. Can you hear? Yeah. Hi, Harry Goldstein, University of Buffalo. Thank you so much for the talk. So if I understood your sort of data, the results you presented correctly, it seemed like there was an edge to the natural semantics, just sort of maybe not as big as you would have expected.
Yes.
And I think, you know, the ultimate interpretation of that in the context of knowing that TypeScript is really powerful and popular helps to kind of explain everything together. So I guess, what is your take on how our kind of practical analyses and analyses of humans and things like that need to kind of feed back into our interpretation of rational programmer results and things like that?
So if I understand correctly, what you're asking is how we take those results and basically we can put them in front of humans to see if this actually matters for the developers when they use them, right?
Talking about in terms of interpretation of the results,
yeah.
I think when we talk about pragmatics, it really needs to be in the context of kind of software engineering and humans.
Yeah.
And so, like, how did you go about that interpretation?
So my interpretation of these results is that given the extreme amount of effort and engineering that is needed to get a sound semantics, let's say for JavaScript, for TypeScript, it may not be that worth it, okay? And given actually the performance penalty that you have to pay because of soundness at runtime, maybe what's worth it is to develop debugging mode. But of course now you have two systems that need to be maintained, so there is a different trade-off here that needs to happen. Definitely, if someone was willing to invest and basically sit down and work all the details of a sound enforcement mechanism for TypeScript and use it for debugging, I do think that that will benefit developers. But there are also economical and practical trade-offs there. So I cannot exactly, give a direction here without taking those into account.
That makes sense. Thank you.
Yeah.
Hi. So this quantitative experiment, right? It started from having this corpus of well-typed programs and then slightly changing them. But that is that's just the normie type errors, right? Like those are the typers that, oh, I passed the lazy by string instead of a string by string. Oh, this should be a hash map instead of a tree map, whatever, right? But there's, of course, a whole other world of type errors where if you had a statically typed system, you would come to this point where, oh, no, this type error means that my whole design is wrong, my assumptions were wrong, I modeled the things wrongly, and there's no way to square this. I have to go back to square one. And this seems to be completely outside of the scope of this.
Yes, up to a point. The errors that we have introduced with mutation, actually there is a whole apparatus to make sure that they're interesting errors. Yes, you are right that those errors basically replace one data structure with another kind of data structure, or basically you may call the function with their own kind of arguments and so on. But our apparatus basically shows that these errors cause ripple effects. So the interesting errors that we choose are errors that basically the value flows a lot inside the program until it actually is being detected as being faulty, okay? But yes, this is a limitation of the study. This is one of the threats of validity, whether we can actually project these results to all kinds of type errors, including the design-related ones that you just brought up. Yes, it's a limitation.
Hi, I'm Jing Yu from the Singapore University of Technology and Design. I'm quite curious about future work in PL pragmatics. Particularly, I think you mentioned like 4 points, and then probably the second half was human factors. So I'm wondering if you were thinking about investigating things like how programming conventions and idioms affect the usage of or the understanding of programming languages.
Yeah, I think what this is actually one of my dreams, to basically be able to conduct a pragmatics experiment about PL expressiveness. And I think this goes towards these conventions, design patterns, and all these other things that you're talking about. I don't know how to do that yet.
Yeah, it would be great to study how design patterns sort of evolve, right? And it's like historical linguistics.
Yes, but I don't know how to turn that into an algorithm so that I can get an automatic experiment. We can do a corpus study. There are other people that are much more well equipped than I am to do this kind of corpus studies. We can do a human factor studies. I don't know anything about humans. Okay, so I don't know how they think. Okay, that's why I'm staying into this pragmatics lane that I believe does not need humans. But yes, it will be amazing if we could figure out how we can turn expressiveness into the examination of expressiveness into a pragmatics question so that we can do an experiment. Yeah.
All right. Thanks so much.
Yeah.
Hi, Michael Koblenz, UC San Diego. Thank you for the talk. My question is maybe a little bit along the same lines. I'm curious, so I've been thinking about the distinction between the definition of a term and the connotation of a term. Right, and if you think about the semantics, they don't really take into account the connotation, right? All the sort of probabilistic information that one gets from the term being used in context. And I think there's a lot of that in programs. If I show you a loop that counts backwards, you immediately think to yourself, aha, there must be some reason why it counts backwards. The programmer wasn't just feeling negative today, right? And so I wonder if you've thought about maybe like an information theoretic kind of approach, where you try to look at some sort of probabilistic notion of what people might infer.
Yes. Actually, I had one of the open questions that I had there is basically formalizing, and I think that's where you're getting at, formalizing the foundations of the rational programmer. And I think that we will need some encoding to do that. We will need some encoding of information. Okay? It will have to be probabilistic somehow because we are modeling basically these agents. I don't know how to do that yet. But yes, that's a very interesting idea.
Okay, thank you.
Yeah.
Hi. Max New, University of Michigan.
Hi, Max.
Hi. So I think this is a great idea because we have a lot of unevaluated claims that we make in the introductions of our papers, but it's difficult for me to see how we could possibly evaluate some of the claims with this approach, right? So when I think about ICFP, functional programming, what is the main thing that we like when we make a good library design, language design, is something like it aids the programmer in modeling the problem, right? So the problem I see is that not just that programmers are irrational, but that programming is not a rational process, it's a creative process, right? And the experiment that you showed, you basically had, right, all the possible designs set up front, right, what the possible types were. So I was wondering, how could you evaluate something like this type system helps me to model the problem correctly, right, where there are many possible different designs, and how could we evaluate those kind of...
I don't know. We will have to talk. Let's pick a particular library. Let's pick a particular model that the library is supposed to implement, and let's sit down together and let's discuss. I think that's why I'm giving this talk.
Okay, thank you.
Hi, I'm Richard Eisenberg from Jane Street. Thank you. Thank you so much for this keynote. I have been, not so much in my sort of research, but in my sort of other work, thinking about pragmatics for a while, and I didn't have a name for what I was thinking about, so I'm excited to have that. There's sort of a step in your talk where you say, okay, we can do these tests by sort of studying human factors, but actually these things here we can do by this other approach. And then that other approach takes years of effort. How have you sort of evaluated the sort of effectiveness of the rational programmer approach, or sort of these more experimental sort of non-human based approaches, to a human based approach, to sort of see if there's one that sort of leads to I don't know exactly what the better outcome would be, but there's sort of two different ways of attacking this problem, and I'm wondering if you've looked at sort of that comparison.
I haven't. My current thinking, though, is that the questions that the rational programmer targets, they're not questions that we can answer by asking humans. And the reason for that is that humans come with biases, they come with hunches, there are a lot of sentimental things that are happening, emotional things when we program, okay? And I want to separate those completely. I'm not sure how, I'm not an expert on human factors, I've never done a human factor study, so I don't know how we could do that, okay? And that's why I went down that path of the rational programmer. The other thing that you said about the effort, yes, it's costly, but it's early. Okay, we have basically 2 dissertations so far spent on that. Okay, I believe that we are making slow progress, and I believe that we will manage to reuse more and more of the infrastructure and get the benefits down the road.
Sure, thanks.
Hello, Dmitry Volkov here from Indiana University. I'm wondering, so the examples you gave here are about how sort of error messages can guide the programmer and basically going from dynamic errors to static errors. But I was wondering how this approach could be generalized to language features that aren't necessarily related to errors.
Excellent. So one of the things that we're looking at right now, the experiment that we're working on actively, is about the interplay between contracts and testing. And we're trying to see what strategies we can use when we're placing contracts in the program to balance the amount of testing, okay? And in this case, the strategies basically involve applying test reduction approaches to figure out how we can replace some tests with some contracts without affecting the quality of the test suite, which we express in terms of mutation testing, of mutation scores. So what I'm saying is that there needs to be some signal about what change we can make to the code, but it doesn't need to be an error. It can be something that has to do basically with some other metric related to the behavior of the code that guides us how we can make the change.
Thank you.
Hi, thanks for the talk. I'm really glad to see pragmatics come up in a PL context. I'm wondering how, so in human factors, or I would think HCI, the sort of bounded rationality model has really like started very early. There's the GOM systems from Stuart Card, and it was abandoned because they really could get no good predictions outside of Fitts law. And this is for like optimizing word processing interfaces. It wasn't, you know, there was no concern about emotional interaction. So I wonder if we should be taking some cues from the HCI community in terms of methods here, if only because they're much cheaper than however many years to do. And I think maybe particularly there, I'm thinking about some of the issues here, even within a rational model of where you draw the bound of bounded rationality. For instance, this model assumes that I don't know the code base and I'm not familiar with it, and I haven't, but this is not how anybody programs. Yes. You're familiar with it and you share, you have build a mental model, but we can't model that in a nice algorithmic way, but obviously that's affecting it significant. So I don't mean that as like a particular critique, but as an example, are these issues that complicate this sort of approach and suggest we should back off methodologically and accept much more imprecision and confounds because we can get more information about our programs, more about what we're doing more quickly? Sure.
I think the difficult part of that question, of figuring that out, is how we can scale. How we can run this, 100,000 scenarios, for instance. We need to be able to.
Well, yeah, but can I just put it in front of 5 people? Will I learn more by doing that?
It is
and it'd be a lot more cheap.
It is quite possible that we can ask people, get some information, and use it to basically refine some of these algorithms, right? But again, I'm not sure if we're getting the same kind of answers to the same questions by asking people and asking the rational programmer. I'm not saying that the rational programmer is the ultimate answer here, right? It's just the beginning for studying pragmatics, and we should refine these models, and this has happened before. For instance, if you see at the use of rationality in economics, okay, there is also behavioral economics now that take bring some of these factors that you're talking about, and they are using them to model things and to run simulations and try to understand how policy affects things. So you're right, there is a path. We're just at the beginning.
Sure, thank you.
Yeah.
Hi, Michael from the University of Cambridge. My question relates to the generalizability of your claims.
Yes.
So there's been some work in human factors or in the HCI community about physics of language design, so trying to find natural laws for programming language design. And the big problem that ran into is that language design is, we've got a tapestry of languages, and it's really hard to generalize claims because the feeling of programming in one language is very different from the feeling of programming in another. And I think, thinking about it, it makes a lot of sense because it's very hard to isolate design decisions because you have to think about the programming language as a whole. If I'm choosing between, for example, delimited continuations or effect handlers, the type system of my language will affect how that, the error messages I come up with, and how the experience of programming with one or more of these features. So I'm wondering how you see your claims generalizing, and whether or not you're thinking about the limits of your approach, I guess, from a generalizability standpoint.
Yeah, okay. You're absolutely right. There is an issue of generalizability here, and I don't think we can make claims across languages. And that's the point I was trying to make here with the difference between JavaScript and Racket, basically. We cannot take the results that we have now and project them into JavaScript. But what we get is basically a blueprint for doing an experiment in a different setting. Okay? By the way, this should not come as a surprise to a PL researcher, right? Because every time we're developing a theory, we're axiomatizing the world again and again, right? And our theories do not generalize the moment we change those axioms, right? Unless if we do it in a very careful way so that the basic assumptions are conserved, okay? So I see this work mostly as, the results, the object results apply directly to the setting that I talked about. They don't go beyond typed Racket and its type system and its enforcement mechanisms, okay? But it's a blueprint that we can use. If someone wants to do, I will be more than happy to see that happening, to apply the same technique, the same method to try to understand the relationship between JavaScript and TypeScript. But generalizations are very dangerous.
We're good. May Milano, Princeton University. I'm continuing in the theme of the last couple of questions. When you're designing a rational programmer to investigate a pragmatics question, part of that design is thinking about what the rational programmer will do, so to speak. That they'll make type changes to try to change a type error, or that they'll edit some code, or maybe they'll look in one file first. And this is another point where we're making some assumptions and we're introducing our own little biases in design.
Of course.
I'm wondering if that's an opportunity for us to go back to human factors.
Of course.
Do you ever intend to, or have you thought about
If I have
introducing...
collaborators, I would love to do that.
Okay.
Okay, I'm not an expert. I don't know anything about human factors. As I said, I would really love to go back to human factors and try some of the assumptions that we use, because they're assumptions based on our own experiences or the theory work that I've done, okay? And of course, we're extrapolating, right? I would be very interested to go back to humans. And besides my own, experimentations with my students, in class and my PhD students, and get something more systematic that I can use to refine the strategies.
Great, thank you.
Thank you for the talk. If I understand correctly, your experimental setup was like you had different hypotheses which were about kind of like you started with the assumption that we have this system of having an untyped like library and then trying to write a typed interface, and there existing bugs basically with that system, and then the hypotheses were different ways to deal with that. And I wonder is there any way you think that you can like broaden the scope of this and say, well, rather than already assuming that we have this system similar to like JavaScript and TypeScript, and we say, well, this already exists, and we're going to try and find different ways to make it easier to work with, to debug. Can you like take a step back and say, well, should we be using like a more rigorous system that wouldn't lead to these bugs in the first place?
Sure. This depends what you're trying to, the question that you are trying to examine. Yes, what you're saying is a valid question. We can try a different design that offers more guarantees and then try and test it and see what's happening. The question that I examined was about this existing system and how it works. And why, I was trying to understand why this system that, from the perspective of theory at least, has no reason to be so successful, is actually successful. But yes, there are other questions that you can ask, and some of them is to examine basically better designed systems.
Okay, thank you.
So thanks for the great talk, Christoph. Thank you for mentioning my old mentors, Jim Morris and Herb Simon. I was wondering, so you talked about one kind of question that we might resolve with pragmatics, but there are lots of others. So one came to mind, the most basic question that we all fight over, typed versus untyped. Could pragmatics give insight into that, and how?
I think we should try to unpack what you're saying. Just like I started with a very vague question and I tried to narrow it down. I think that's the process that we need to follow here in order to take what you're saying about typed versus untyped languages and the benefits and in which contexts they help and how they help. And that's research. But I do see it within the scope of pragmatics, and I do think that the rational programmer could help somehow this.
Could you give an example of an unpacked question that you think we could get insight into?
So, for instance, let's say we have certain transformations, right? And we have programs in typed languages versus programs in untyped languages. If we have a collection of transformations, how can we use those transformations in one setting versus another to refactor our program without affecting the result of the program? And
maybe we can discuss this further.
It would be, yes. I'm sorry, I don't have a, what you're asking basically is a research question, right? And I have not done the research, so I cannot say something specific, right? But yes, it's a very interesting question. As it's also a very interesting question how we can go not talk about mixed type systems, but about actual type systems and the errors that they give. Okay? There are ideas out there, like delta debugging, for instance, that has been used successfully to track down the messages, the sources of type mistakes. Can we examine, based on delta debugging, the design of error messages or error reporting mechanisms of static type systems with the rational programmer? I don't know, maybe.
Thank you, Christos.
Thank you.
Finally, I'm loud here. Thank you, Christos, for this inspiring talk. I think Christos will be around for a couple of more days. Yes. So if you have more to interact with him, grab him, propose new problems, and I guess he'll be more than happy to talk to you.
Of course.